So this is the third lab in this module. So the advanced training optimization using Lightning. So here we we're talking about um, making deep learning training more memory efficient while still keeping good models performance. So here we're talking about two major optimization techniques. First is mixed precision training, and the second one is gradient accumulation. So here's a big picture of the goal of this laboratory. So the GPU memory is expensive. When training deep learning models, especially large ones, you often run out of memory before you run out of compute power. So there are different ones. Um, Run of memory and run of computational power. Computational power is more on hardware, but the run out of memory is more on software. So so this laboratory teaches how to reduce GPU memory usage, still keep high accuracy, benchmarking experiments properly, use Lightning professionally. So what we build in this laboratory? So we build a full benchmarking system that can train models, measure GPU memory, um, measure validation accuracy, compare optimizations techniques, and visualize trade-off. So here the full goal is the full benchmarking system, not only models, but we train models to measure GPU memory, measure validation accuracy, compare optimization techniques, and visualize trade-off. So the part 1, we import of course the what we need, like torque, Lightning.pytorque, torque vision, torque metrics, and some helper utilities. So some of the important lines, we use the code torque.setFloat32 precision is equivalent to medium. So this tells use a slightly faster matrix multiplication strategy. It improves speed performance balance. Next is Lightning data module. So the notebook creates Cypher 10 data module based on Lightning's P1.Lightning data module. This class handles downloading data, preprocessing, train loader, validation loader, batching. So the dataset we use is Cypher, which contains 10 images class total, like airplanes, cars, birds, cat, dogs, etc. Why Lightning data module exists? Normally in PyTorch, data loading code becomes messy. Lightning separates it cleanly. Instead of mixing dataset logic, batching logic, model logic, everything gets modularized. And Lightning module, and the notebook creates Cypher 10 Lightning module. So based on PyTorch Studios, we have P1.Lightning module. This contains the following: model architecture, optimizer, loss function, training step, validation step. So we have the CNN architecture, the convolutional one. The model uses convolution layers. Like we have the layers for the first convolutional layers is 32 feature maps. The second is 64. The third is 128. Then fully connected layers 512. Why this architecture was chosen? So this was the efficient configuration discovered earlier in our previous lab, meaning good accuracy, reasonable memory usage, reasonable speed. Next is building the benchmarking framework. This is one of the most important sections. So it creates reusable system for experiments. Instead of manually training repeatedly, it automates everything. So we have the callback system. Lightning has something called callback Callbacks. Callbacks are special objects that hook into training events. Example, before training starts, after validation ends, after epoch finish, and like performance callback, its job is track to validation accuracy and track peak GPU memory. So the callback is to track from before training starts, after validation ends, and after epoch finish. Why peak memory matters? So GPU memory usage is usually the bottleneck. Even if a GPU is powerful, if memory is full, training crashes. So measuring peak memory MB is extremely important. Next is callback life cycle. The callback uses these hooks. On train start, first the on train starts. What does is runs before training begins. It resets GPU memory statistics, and next is on train end. It runs after training ends. It records maximum memory used during training. Next is validation epochs end runs after validation. It stores validation accuracy. Why this is powerful? Instead of printing random logs manually, everything becomes automated, standardized, reusable. This is professional ML engineering practice. Next is the trainer. This is the heart of Lightning. The notebook creates run training. Inside it, there's a trainer from Lightning. What trainer does? The trainer automates the entire training loop. Without Lightning, you'd manually write for epoch, for batch, optimizer.zero grad, loss.backward, optimizer.step. Lightning handles all of that. You only configure behavior. So the important trainer parameters is the notebook focuses on two important settings. First is precision. We set it or initialize it to 32 dash true, or precision equivalent to 16 dash mix. This controls numerical precision. Next is gradient accumulation. Accumulate grade batches. It controls how many batches accumulate before weight updates happen. So here's the part 6, mixed precision training. This is the first optimization technique. So the standard precision, normally deep learning uses float32, which uses 32 bits per number. Advantages is accurate and stable. Disadvantages is high memory usage. So in typically deep learning, we converted the original value to the small ones. That's why we use the floating value. So like float32, that's approximating the accuracy of the particular number. But if we use the smaller ones like float16, it reduces its accuracy to the real number. Next is mixed precision. Mixed precision combines float16, float32, and the GPU intelligently chooses which operations can safely use lower precision. So why this helps? Smaller numbers use less memory. So GPU memory decreases, training speeds up, larger model fit. So here's the Lightning setting. So the precision equivalent 16 mixed enables this automatically. Lightning internally manages autocasting, gradient scaling, numerical stability. So and why mixed precision exists? Pure float 16 can become unstable. Some values become too tiny. So Lightning mixes fast float 16, stable float 32. Best of both worlds. So the trade-off advantages is less memory, faster training, but the potential disadvantages is slight accurate drop, possibly instability. Next is gradient accumulation. This is the second major optimization. So the core problem that the gradient accumulation solves is like the large batches size improve training stability, but large batches requires lots of memory. So let's say we have the batch size of 256 may not fit into GPU memory. So the solution is gradient accumulation. Instead of processing 256 samples at once, process smaller mini batches sequentially. Batch 1 compute gradients, batch 2 compute gradients, then update weights after that. So the effective batch size is, so the formula is equivalent to batch size times gradient accumulations. That's the effective batch size. Example, we have the batch size of 128 and the gradient accumulation is 2. So 128 times 2 is equivalent to 256. So the model behaves similarly to training, which batch size 156. Then why this saves memory? We never load all 256 samples simultaneously. You only load smaller chunks. Therefore, lower memory usage, but similar training behavior. So the important trade-off, gradient accumulation can improve convergence, stabilize training, but training becomes slower because optimizer updates happens less frequently. So it tries the experiment. We have the batch size of 128 and 2. So the effective batch size is 256. Let's say we have the experiment number 2. So the batch size is 64 and the gradient accumulation is 4. So we just multiplied it to 4 and still have the 256, same effective batch size, even less memory. But there's a drawback about that because there's a lot of it saves memory and there's a lot of steps like 4. So the time will increase also. Why smaller real batch size saves memory? Because GPU memory depends on actual loaded samples, not effective simulated batch size. So real batch 64 uses less memory than real batch 128. Next is combining both optimizations. Now auto combines mixed precision, gradient accumulation, combined strategy, precision 16 mix, and gradient accumulations too. So this gives memory reduction from mixed precision, large effective batches from accumulation. So why this is powerful? This is commonly used for transformers, large language models, state-of-the-art models, especially when GPUs are memory constrained. So the final combined experiment is, and the notebook also tries batch size equivalent to 64, gradient accumulation is 4, precision is 16 mix. This becomes extremely memory efficient. Here's the part 9 result analysis. The notebook then compares all experiments, metrics compared validation accuracy, how good the model performs, peak GPU memory, how much memory training consumed. Observe results. The notebook concludes mixed precision reduces memory, usually keeps similar accuracy. So a smaller batch plus accumulation, it reduces memory further, so it keeps effective large batch training. Combined strategy gives the best memory efficiency without significantly hurting accuracy. So the most important engineering lesson is, so there is something bigger than just optimization. Benchmark everything. Do not assume. So measure memory, measure speed, measure accuracy, and measure the trade-off. This is a real-world machine learning engineering. So the lightning concepts we practice is lightning module, lightning data module, trainer, and callback, mixed precision, gradient accumulation, benchmarking, experiments. These are the core professional lightning workflows. So real-world industry usage. So these exact techniques are heavily used in OpenAI, Google, Meta, Nvidia, because training giant models without memory optimization is often impossible. So you can think of the two optimizations like the mixed precision is use smaller number representations to save memory, and gradient accumulation is pretend you have a larger batch without loading everything at once. And combined, use both strategies together for maximum efficiency.